A data is this thing, and operation add created by operation add, that's correct, and B data is also created by operation add, which is not true, right? So let's check what's wrong. Sir Matmal, something is wrong here, and output shape equals what? A rows versus B columns. This is correct. Parents, we initialize the parents. We we added the parents over here. Requires grid equals true, that's right. And then we have output size equals what? Out size equals this. A shape 0, B shape A rows, B columns, which is correct. So grid would be out times this, and visualize the operations structure. Tensor matmal backward type equals tensor matmal. It should be matmal. Okay, and how about add? Tensor add. This is op add. Matmal. Matmal is what? Add op add. Okay, so if I see the tensor structure has add matmal. Yeah, what exactly is wrong? So we have b equals matmal a and zt, and can we print z over here, b over here? So tensor get data of b. So get tensor get 2d. Okay, there it is, the tensor, and we have metadata for a. It has tensor id. Ooh, tensor IDs are same. How? Something's wrong. Something is wrong. Tensor add. What does tensor add do? So tensor add, does it increment the ID? Yes, it is incrementing the ID. And how about tensor matmal? It's also incrementing the ID. Correct. Add just increments the global tensor ID. This also increments the ID. Why the IDs are same? Why the IDs are same? These two should not be same. Maybe because something is wrong with ZT, I guess. Yeah, so let's check the transpose method, because see what's happening over here. So we are computing this first tensor using tensor add, which takes x and y, which is correct, right? So x and y both require squared equals true. So once one requires squared equals true, then only it populates the metadata. For example, if I show you like here, tensor add. All right, you see, if requires grad equals true, then only it populates the metadata. But the problem is we are incrementing this ID before this, right? So this should increment first, and then it should like show us this metadata or whatever, right? Yeah, that's important because we are actually incrementing this ID before the metadata, right? So if the problem is here, okay, no worries, it's understandable. But if it's like repeating the tensor ID, then there is definitely a problem. So let's just verify if requires grad is working fine. So if I first, before going to print a, let's say A and Z T metadata, right? So let's just print A and A metadata, and this is going to be like Z and T metadata. So this is ZT. So let's just print if any of them requires grad equals to A or ZT, then B will require grad equals to. And this is what matmul function says over here. Let's check one more time. So we have tensor matmul, right? And you see the condition is if A or B requires, if any of the parameters requires grad equals true, then the output will require grad equals true, right? So let's just see what's the status of both these parameters. So if any one of them is an OR condition, if any one of them is true, then the output will be true. But for the sake of like for sanity check, what we're doing is we're checking for both. So this is metadata for A and this is for ZT. So it requires grad equals true and requires grad equals true. So both of them requires grad equals true. So the result should be like this. B definitely requires grad equals true, right? So the problem is not with the B. The problem is not with the B, right? And if you check their IDs, let's say if you check their IDs, they're being assigned by ID 3 and ID 5. This makes sense. ID 3. Let's see what transpose does. Decision increment tensor.c. This should also increment because at the transpose method we are returning some new out tensor rather than the existing tensor, right? So transpose. Let's just see if that increments the global ID. It's not incrementing. Like, are you serious? Yeah, TID global tensor ID increment, right? And let's just see now what happens here. Does it make any change? Well, the ID has been changed. This is 4 and this is 6 now. So it's taking this ZT tensor as a new tensor, right? And that's how we can actually backpropagate. So it has gradients equals true. Now it is giving me the exact method, and previously it was also working fine for transpose. It was working fine for transpose, except the ID has changed, right? And now, if I check for B, metadata for B, and let's see what happens. Oh my god, it worked. So that was actually the problem. This is where our computational graph was breaking, right? Yeah, that's fine. So we understood. Now the ID is 8, and so in case if at any particular tensor node, if you broke your logic, your computational graph will be broken, right? If you break your logic with metadata or whatever. Perfect. So now let's see for both. So tensor C, and this is for A, and this is for B, right? And let's see, backward function equals to. Perfect. And we have meta 8 tensor ID 6. Yeah, makes sense. So tensor ID 8 because Z transpose is not shown over here. It should not be 7 because Z transpose has some ID and then it adds up. And then we have 16 cross 16, and then we have stride shape, and then we have tensor dimension requires grad op times, and backward function, which is actually the matmul if you compare from here. Dot h. So this is 0, 1, and 2. So matmul is this. In case if you cannot see it, let me just make the font a bit bigger. Okay, makes sense. Makes sense. Now, let's just add one more thing. So tensor metadata meta. Okay. So what we are doing here is we are just backward function x operations type. This is not type. Okay, and what if I go like printf backward function pointer or back pointer? Let's just do it like this. P, and let's just say this is going to be operations backward. Will it give us something? Oh my god, it's giving the pointer location, right? Yeah, it's giving the pointer location. It's giving the pointer location. So can we like decrypt that? Dereference that pointer? Let's just see. So we have y tensor metadata. So if I go like alright, so if I go from here to here, backward function, pointer, and this is dereferenced version. Let's see if it works. Nope. So it's giving me this exact location of the pointer, where that function pointer resides, right? So, yeah, this is actually the metadata. So now we can actually traverse the graph, right? Alright, so we can traverse the graph now. We have successfully built the computational graph and we need to traverse it, and by traversing we will be like visiting each and every node, whether it's a tensor or whether it's an operation node, and then if it's a tensor and if required squared equals true, we can update the gradients, right? And gradients are calculated using the chain rule. So let's just try to build a graph. We'll be using DFS for now, or depth first search, and then we will traverse each and every node and see that how we are going to populate its parameter, that is grid parameter, right? So let's just without a further delay, if I sort of add a graph here, so this is going to be wide DFS, and it's going to take tensor, that is going to be root tensor, and visited list. So bool visited, right? And then if visited at root ID, if it's already visited, then return, else show its metadata, show metadata root, and if root has parents, then find the number of parents, and p equals root parents, and then for int 0 I less than p. This should be recursive DFS function parents I and visited, right? Alright, so this should be it, and then yeah, fine. This is one thing, and then we need to find actually the depth. So size t depth is going to be global id, and if while 0, what you should do is DFS like b, which is actually the last node over here, and then depth, and then decrement depth, right? And then sorry, this is related, And let's define visited over here. So visited pool visited. Um, let's just say int it should be all the like length of all the tensors that we've created so far. So global tensor ID, and let's just populate it. Okay, so let's just define this like this, and yeah, so false, right, and all zeros initially. So what happens now? Is that it? So we're calling DFS while depth greater than 0. So until the depth equals 1, that is, we reach out the last answer. Let's just see if this works. What's wrong? Parents, root parents. Should be root parents instead of parents. Wait a second. Root parents or parents? Yeah, root parents. Yeah, we're getting something. Let's just add some formation over here. So DFS in DFS function, when we just print this, okay, so let's just format this a bit so we can understand what's going on, like so. And now we have tensor ID equals 8, which is actually the last tensor, and it has dimension this. It is obtained, created by optimes, that's right, and backward function is like this, backward pointer is this, number of parents 2, and then we have tensor 6, right, tensor dimension equals 2, and this is A, right, tensor ID 6, and then we have tensor ID 0, and it just requires squared equals true. So we're trying to access some memory at the end, which we should not, right? So yeah, so it is traversing the some nodes, but let's see what the error is, and let's see what's wrong with our this method. Because see, how many tensors do we have? We have all these tensors, right? So this one, right, x, y, z, a, b, and c. So have we visited all these nodes? That's the question. Okay, let's just check this out. Okay, so if we run it again, we see that these are the tensors that are getting printed. Something's wrong. Something is wrong with our function. If visited return, oh dear. I never set visited equals true, which I should. Yeah. Yeah, that's the problem. So just remove this, bring it all over here, and visited root ID. Should be true, and then Let's see what happens now. Okay, so still three tensors. I think this is incorrect. I should not like put it inside while because it will keep on visiting the same root node, right? Right, and 6 8. Tensor metadata. Okay, so in case of leaf node, we're not printing anything, right? So printf leaf node. Operations. Yeah. Uh, okay, so let's just comment this out for now. Yep, we are getting this now. So previously we were getting only um, three tensors. Now we are getting 1, 2, 3, 4, 5, and 6. Alright, so these are the 6 tensors that we initiated, and looks like apparently our DFS is working fine now. So it's visiting all the nodes and splitting their metadata. So now it's just a matter of, let the gradients flow backward, and at each node just store their derivative information, which will be uh, calculating using this kind of chain rule. I'm not saying formulas because we're not using the exact same formula. It depends what the operation is actually. If it's like plus operation, you just want to copy the exact same gradients that are coming to the next nodes, right? And if it's matmal operation, you sort of multiply with respect to function wise, with respect to parameter wise, both of them. So you take partial derivative and then multiply both of them, right? So it depends on what type of operation it is, and looks like we have successfully traversed our computational graph. One thing that I want to do over here is I want to put another check. So if root is null, um, return, right? And yes, this looks fine. Metadata, this also looks fine. And now we don't see any segfault root. What's wrong? Uh, uh, equals null and return. So perfect. And one more thing that I want to do is tensor.c void, and I think I should come over here and do not dereference this. I don't just need this even. I don't even need this. So tensor dimension, tensor gradient, leaf node. This is a leaf node, and once the operations are true, that means that it's a derived tensor. Um, so if it's a derived tensor, then it will print the operation that is used creating that tensor and its parents. So this is also leaf node, this is also leaf node, and it has two parents. This is created by op-add, and then we have a this one op transpose, right? Yeah, yeah, this is the one op times. So I was looking for this one. Excuse me. So this has backward function equals to, which should be matmul, and if we cross verify this, um, it should be something like this: 0, 1, and 2. This is matmul operation. Fine. So git add, git commit um, and if graph traversal logic method for for Autograd. Okay, so this was it for this video. Hopefully you have learned something. That's how we actually traverse the graph backwards. So you just need to have the concepts of how DFS works and how to create nodes that are interlinked and then traverse them, right? So this was it for now, and I will see you in the next one.